So while she's setting, I'll go ahead and start. Jeff Glass, Pratt School of Engineering, Electrical and Computer Engineering Department, but I'm really a material scientist. So a lot of what you'll see me talk about is the material side of what we do. We also have an instrumentation side in my lab, which you'll hear about a little later from one of the other speakers in some of the systems we're putting together. And if I have time, which I probably won't, I'll also give a slide or two about that at the very end. So let's see if... Okay. On this, but not here, so I will keep my eye up here. Okay, so real quick, it's not me, it's everybody else. Just the funding and the collaborators and the students and postdocs, of course, are really who make all this happen. I won't spend any time on that, but I want to make sure that we understand that. Capabilities are probably more important today than the specific results. And so the capabilities that we have that we love to collaborate on are listed here. A plasma-enhanced chemical vapor deposition of thin films in various materials, especially carbon-based structures, atomic layer deposition of oxide materials, in vacuo X-ray photoelectron spectroscopy and ultraviolet photoelectron spectroscopy. How do we understand material surfaces without contaminating them, if you're not familiar with those techniques. And then a lot of electrochemical techniques, which translate into a number of different energy applications. And they go from the electrochemical impedance spectroscopy all the way down to photoconversion efficiencies for solar fuel generation and that sort of thing. And then with RTI, as a close collaborator, we do a lot of microfabrication, and I'll talk a little bit about that. Okay, so some of the structures that we grow, these are carbon nanotubes. So if you look at the micron marker here, these are bundles of thousands of nanotubes that are selectively deposited in these bundles for specific reasons and specific applications. And here are just a lot of cool structures. This is really why I'm into material science, is to look at pretty pictures. And these are some of the neatest, I think. We also grow graphene, and these are graphene flakes. So graphene is just a single sheet of carbon, and these have very specific properties that allow us to do energy conversion and storage more effectively than other materials. So we utilize these structures combined with the carbon nanotubes that I'll show in a minute to get the special properties of energy conversion and storage. Here is a MEMS fabrication, where if you look at this micron marker, these are really tiny panels that we flip up to be lateral devices on materials that allow us to make materials in a very small scale, as opposed to what you would traditionally see in material. Here's our kind of our bread and butter right now, and that's graphinated carbon nanotubes. So we grow graphene foliates or flakes all along these carbon nanotube structures. So we have a carbon nanotube, and then we grow these flakes, and that gives it much higher storage capacity for energy storage and gives it much higher catalytic capabilities for catalysis. Here, there's a lot here on this slide, but I really want you to concentrate on this lower right-hand corner. This is considered this x-axis, the number of foliates, or the number of graphene flakes on it, and based on deposition time, and then capacitance. And we see about a 5 to 7x increase in various types of capacitance that are allowed by this graphinated structure, as opposed to a carbon nanotube structure without the graphene flakes. And this is a new material that our lab invented a couple of years ago. And we also find the same thing with the catalysis. This is shown here, where we're looking at just a ferrocyanide couple, and we see that the carbon nanotubes have a very strong separation between the redox couple. And when we put on the graphene foliates, that redox couple comes closer together, so more reversible, faster reactions. So that can be for any kind of catalysis, and it's been shown for a couple different types in our lab. We also look at solar fuels, meaning generating hydrogen and oxygen, and we do that with lots of different structures, but some of the most interesting, I think, are these nanoparticles of FTO covered with a very, very thin, like an atomically thin layer of oxide, which is TiO2 in this case, that allows us to get a much better conversion of the sunlight to the chemical. And so shown here, when we use our new structure, we kind of combine the best attributes of the nanoparticle structure and the TiO2 structure into this conversion, and here we have the conversion efficiency, across a long wavelength as opposed to in a very narrow range. So higher catalysis of the solar fuels, a higher catalysis rate. Two applications I'll end with is miniature mass spectrometer for methane detection. Rogue methane at wellheads and at refineries are a big problem for the US and for DOE. And we're trying to develop a better spectrometer, or developing a better spectrometer based on new materials and on what's called coated aperture spectroscopy. I won't talk about that much. Electrochemical disinfection for an energy neutral off-grid toilet for the developing world is the other area that we're working in. And in the last 15 seconds, I'll show you a schematic of the mass spectrometer, normally the size of this table, now shrunk down to the size of a shoebox because of the coated apertures and the microfabrication that I talked about earlier. And then I'll end with the beautiful pictures from that, where a normal spectrometer has a slit, and you get this very, very poor signal because you've thrown away so much of the signal. And with our new spectrometer, the coated aperture spectrometer, we have a 10x to 12x increase in the signal, and my time is up. Thank you.
My name is Nico. I'm an assistant professor in mechanical engineering and material science, and a lot of the work that we are doing is on hydrogen production, for example, with catalysis powered by sunlight. Yeah. So a lot of the work that we are doing is on producing hydrogen by steam reforming. If you have not heard of that, that's actually the most conventional way of producing hydrogen. More than 90% of all industrial hydrogen production today is by converting a hydrocarbon fuel like natural gas, methane, or alcohols to hydrogen-rich gas. These reactions happen on a catalyst at very high temperatures, several hundred degrees Celsius, 200, 700, 900 degrees Celsius. In other words, they are very thermally expensive. They require a lot of heating to get to that temperature and to the chemical reaction. We want to do that in stationary, small-scale applications where we use sunlight to convert an easily storable, transportable fuel to hydrogen and then use it in a fuel cell. But that's not just my crazy idea. Hydrogen is being used in fuel cell more and more in real applications. Since last year, you can buy and lease Toyotas and Hyundais in the US that run on hydrogen with fuel cells. I have not seen a gas station that has hydrogen written on it yet, so that's why we think it's interesting to work on that. In an early project, we developed these conventional-looking flat-plate solar collectors where we achieved high temperatures of above 250 degrees Celsius. That's at least 100 degrees Celsius higher than conventional flat-plate solar collectors that you can buy today. And that's high enough to produce hydrogen from methanol with high efficiency and very high power densities. The problem with this is, since it's relatively large, we have large heat losses, so it's not very efficient. And to improve that, we are looking now in a much more fundamental study, collaboration between myself and Dr. Wadin in biomedical engineering, partly funded by the Duke Energy Initiative, on how we can use plasmonic heating to heat our catalytic nanoparticles, and only those, without having to heat the entire system. So we use plasmonic substrates in this case that have a plasmonic heating in the crevice of these two hemispheres here, and we try to see if we can get enough temperature here to power methanol steam reforming, which requires at least 250 degrees Celsius. Keep in mind that the whole fuel, the whole substrate, everything is cold. We are at room temperature, but only locally down here we want to achieve temperatures that are high enough to drive chemical reactions, in this case, hydrogen production from methanol. The way we do that is we take these plasmonic substrates that we get from our collaborator, Dr. Bodin, polystyrene spheres on a substrate. They're on 0.5 micron in size, coated with a thin layer of gold on top. And as you can see here in this COMSOL simulation, we have about a 7-8 times increase in electric field in the crevice down there in a very small spot of maybe 5 to 10 nanometer in size. We were not sure if that works because nobody ever has done that before, but we deposited our catalytic nanoparticles on top of these spheres to get this relatively rough, dirty-looking substrate here. And the good news is we got temperatures that were high enough to achieve chemical reactions. So we use it under full spectrum light. We concentrate it with a moderate solar concentration of 12 to 56 times. It's with a very cheap Fresnel lens. We put the whole substrate in liquid water methanol, and then we don't heat it externally at all. The whole reactor, the fuel, the substrate, everything is below 30 degrees Celsius, so very cold. But locally, apparently, we can achieve temperatures above 500 up to 600 degrees Celsius, depending on the size of these hotspots. That's the number I said you before of about 5 to 10 nanometer. We don't know exactly what it is, but it should be in the range of 5 to 10 nanometer, achieving these 500 to 600 degrees Celsius. Very important result here is we can achieve these high temperatures at solar concentrations of 30 to 40 times of regular solar light, which is very low, which can be achieved very easily in realistic systems. With that, we can achieve hydrogen production rates of 30 liters per hour per meter square, which is pretty good considering that we actually only use these small spots. About only 1% of the whole substrate is at the moment usable. If we can find ways to increase the size, the surface utilization, we can achieve much higher gas production rates anyways. A very important result for us in contrast to what Dr. Glass, for example, said before, we see here an exponential increase of gas production rate with concentration, which indicates that it's actually a thermally driven catalytic reaction. There is no electron-driven chemical reaction in this case happening here, in contrast to water splitting systems to that. And I made it to exactly my time.
Good morning, good afternoon. Sorry, my name is Adrienne Stiff-Roberts. I'm an associate professor in electrical and computer engineering. And today I'm going to be talking about some work we've been doing in my group on tandem solar cells by RIR-Maple. So hopefully if you know at the end what a tandem solar cell is and what RIR-Maple is, I will have done my job. So this material system that we're interested in depositing with this RIR-Maple are basically materials that would be useful for organic and hybrid solar cells. And what we mean by that in this case are essentially solar cells that are made out of plastics. And so why would you want to do that? I think the main reason you'd want to do that is you could deploy these materials in very interesting ways. They're flexible. You could do roll-to-roll processing, which might be very large area and inexpensive. This is a mock-up that I found that's basically a bus stop of the future. So you have some organic solar cells, an organic display, right? So using plastics that can integrate with glasses in order to do functions that we typically associate with silicon right now. I mean, this is just a picture of a pretty solar cell panel. So it's not really functional, but it is nice to look at it. Things are just the beginning. And also integrating these things into clothing. So where does that stand? I know this is a bit busy, but I'll try to help. So silicon, crystalline silicon, that's what we're usually familiar with integrating solar panels onto our homes. And that's the solid square here without a concentrator. And the efficiencies are about 25%. And the first silicon solar cell was demonstrated in 1954. And got to about 25%. Now, if we look at different material systems like compound semiconductors, these purple devices, like this single crystal, that's getting to about 34%. This is what's in space satellites. This is the type of solar cell that they use. And if you use a concentrator, you can get efficiencies up to about 40%. But these are too expensive to use on Earth for the most part. So emerging solar cell materials are based on these organics and hybrid materials. Now, they're much lower in terms of the device efficiency. Sort of your standard solar cell is around 12%. But what I forgot to mention here, so when you have these concentrators, the space satellites, they also have multi-junctions. So they have multiple solar cells that are stacked on top of each other. That's one way they increase the efficiency, and they do that because they can absorb more of the solar spectrum, more colors of the sunlight. Okay? So if you try to make a tandem solar cell in the organics, you actually have lower efficiency than if you just had a single junction. So why is that? A tandem solar cell then is two different solar cell active regions that are stacked on top of each other, and there's this intermediate layer in between that's extremely important to the overall device performance. So while this has been figured out for these satellite systems, doing this in organic materials for terrestrial applications is challenging. So in my group, we're looking at this deposition technique. It's called resonant infrared matrix-assisted pulse laser evaporation. It's basically a laser-based deposition tool for depositing plastic films. It gives us much more control over making these devices and also determining what this intermediate layer is. So in my group, we've just started looking at some of these devices and basically trying out different types of intermediate layers. And I'll just tell you a little bit about how this maple works and what's different about it. So it's basically a variation of pulse laser deposition with two big differences. One is that it uses an infrared laser, so you don't damage these organic or plastic materials that you're trying to deposit. And the other big difference is that the target is actually a frozen emulsion as opposed to a solid polymer target. So these are very unique features that enable us to combine different materials even when they have the same solubility. And that's really important for this tandem structure because you have all of these organic materials that you usually make in solution. But if you try to build up a stacked layer where everything has the same solubility, when you put down the top layer, you actually mess up the bottom layer. And so in looking at this, then one thing that we think we can contribute is looking at different types of intermediate layers for these tandem structures. So through a seed project that we received from the Energy Initiative and working with Mike and Mickelson in the physics and electrical engineering departments, and we started looking at silver nanoparticles that were deposited by Maple. And so actually demonstrated a lot of important capabilities with this project. One is that using the Maple process, we can deposit these films on just about anything. So scotch tape, glass, aluminum foil, paper, silicon, parafilm. So the process works the same way regardless of what your substrate is. And in a lot of chemistry applications, that's actually a very unique functionality. And then we also showed that we have very regular control over the surface coverage of these nanoparticles. So controlling the concentration of our target or controlling the deposition time, we get very regular behavior in terms of how the surface these nanoparticles cover the surface. And then finally, we can demonstrate that for these different coverages, we get enhanced absorption in a polymer film. And that's based on this idea of plasmonics, or the special interaction between a metal and a dielectric layer, in this case, the polymer. So controlling the coverage controls this enhanced absorption, and we think that will help with the tandem structures. Thank you.